so we can start. So it's the last lecture, and as I promised, I will tell you a little bit about inequalities, about the test of inequalities, and a little bit about quantum cryptography. Because of all these schedules, travel, and so on, this must be the last lecture. I will tell you what I will not cover because of this, in some sense, limited time and various limitations. Talking to you, I realized that even though, of course, each of you attended quantum mechanics courses, there seems to be very little understanding of collision theory, of scattering problems. And some of you, I would say most of you sitting here, attended my lectures last year on gases, and there I briefly discussed this because this scattering of very slow particles is of great importance for this called atom physics. But there I somehow tacitly assume that you know a lot about scattering theory. So it would be most appropriate if there was concise but more or less complete section on scattering in this course. Fortunately, there won't be one, and I apologize. Actually, you've got some of you, all of you, you've got my lecture notes, which are called Quantum Lecture 10. I have one more. Lecture X. It's 10. Yeah. I have one more already, and that's about collision theory, but that is also brief. So even if I forward this to you, it will not be a replacement for the good lecture. Okay, so let's go back to what I promised to cover. And let me start with something almost everyone knows. There are some crystals, like calcite is a good example, which what optics people are calling birefringent, which means that the refractive index inside depends on the direction of polarization of light. So this sort of light travels one way, and this sort of light travels some other way. And it is very easy to understand that if I have a classical wave impinged here, and perhaps it is polarized in yet another direction, not in one of these eigendirections of this birefringent crystal, then this vector of polarization I have to project both on this vertical and on the horizontal and on the vertical axis. And cosine of this angle squared would tell me which fraction goes which way. This is kind of obvious, and it carries nothing more but just the information that there is a linear space, so to say, behind the classical theory of classical electromagnetic waves. And as we already know, one can perform experiment with a birefringent crystal, which would be with the input with single photon states. So I have the same type of crystal. I send in this tilted polarization photon, but a single one, and we know that this single photon is not divisible. So either it will go one way and emerge here, or go the other way and emerge here. Moreover, you probably understand that quantum mechanics can tell us some probabilities of telling, depending on the angle, yes? Telling whether the photon will end up here and here. Suppose we are at 45 degrees, and suppose these probabilities are equal. Okay? And then this poor guy, this photon coming here, faces a dilemma, which way to go. Orthodox quantum mechanic person would answer this question, which way photon will go, will answer this, well, nobody knows and nobody will ever know. It's just basic randomness of quantum physics, reflected by the fact that this photon is not split into two, and only with some probabilities always fully emerge either here or here. But that is really the clue, the basic aspect of quantum physics, namely that this randomness seems to be inescapable. Unless photons that are polarized this way are somehow basically different than photons that are polarized this way. Unless there is some way of labeling photons, I'm vertical, I'm horizontal. Unless, what people like to call it, unless there is some hidden variable that can take perhaps two values, 0 and 1, and depending on what our incoming photon, what value of this hidden variable is sitting on this photon, it will go either this way or that way. So this dilemma is really almost the essence of why quantum mechanics is weird. There are other things, entanglement, correlations, Bell inequalities, something that I will tell a little bit later on. But the main idea, the main dilemma is here. Okay, so for a couple of decades, ever since this famous paper, which is called EPR paper by Einstein, Rosen and Podolsky and Rosen, was published in mid-30s, people were debating this question whether there is something behind quantum mechanics which is more deterministic than quantum mechanics is. And it looked like this question belongs in philosophy rather than physics. Question belongs to physics if one can answer this question using ideas and derivations, or better still, using experiment. And it was not until the 60s of last century that John Bell, Irish physicist, actually elementary particle physicist, had an idea, derived these famous inequalities, had an idea to distinguish between true full randomness of quantum physics and the presence of these hidden variables. And I will tell you now what is the original idea of Bell, and we will derive the original Bell inequality. So, the problem in question is the following. Suppose we have a source of photons, of particles. You can think of particles, spin 1/2 particles, which can be a source of a pair of particles that has total spin equals 0 and projection of the spin on some axis also 0. In other words, you remember that when we had a system of 2 1/2 spins, there was a triplet state with a total spin equal 1 and then 3 components, 1, 0, and -1. And there was one so-called singlet state, which had both global angular momentum quantum numbers 0, 0, and 0. Now this 0, 0 state has zeros, is rotationally invariant. It is not really depending on which way I put my so-called quantization axis. So suppose I put it somehow, and then whatever the direction is, you probably remember that the state is having the following form. It is plus a half for one particle, minus a half for second particle, minus minus a half for the first guy, and plus a half for the second guy. So as I say, this is the singlet state, and I'm sure you all know it, especially those who attended this famous little exercise that these guys were conducting here a couple of weeks ago, and that's it. Good. So when I have this state, and I do measurement in some direction, called this direction z. On one side here, just check what is the value of a spin in z direction. By z direction, I mean the same direction in which this has been written this way, yes? Then what is the result? What is the p plus and p minus at direction z? Well, I have to project this with respect to this plus, yes? So this goes away, yeah? And then sum over two possibilities of this fellow, but there's only one possibility. So I get 1/2. Okay. Equally, the other guy is also 1/2. Sure. No puzzle, obvious. Now, what I claim is that if I do not take z direction, but if I take any other direction, absolutely the same is true, just because the state is rotationally invariant. It has this form regardless the direction of quantization axis. Now comes what is really important for Bell inequalities, and these are correlations of measurements done on this side and on this side. So in other words, I put my quantization axis, so to say, in one direction here, and then some other direction here, which is at the angle of theta somehow. I don't even write theta, which is b vector, yes, and this is a vector. Yeah. So if a vector I choose as a z axis, then of course all this basis plus half minus a half applies, and this is kind of obvious. What I have to analyze a little bit is how the operator f of b looks, which is the same as b times sigma, yes? I just project it now on the b direction. And of course I do not need to work in 3D space, because obviously I can always put the x-axis in the same plane, which is already spanned by a and b. So in other words, I can write this b times sigma in a form cosine theta times sigma z plus sine theta times sigma x. Yeah, I do not need y. I could put it, but then I would make my life more complicated, yeah? So what sort of matrix is it? We remember that sigma z is 1, 0, 0, minus 1. And we probably remember that sigma x is 0, 1, 1, 0. So when I combine everything, then my b times sigma is is the matrix cosine theta, sine theta, minus cosine theta. I can always diagonalize it. I can find eigenvalues, and everyone can guess what eigenvalues are.
1 minus
1 and minus 1, sure. So there is a plus 1 eigenvalue and minus 1 eigenvalue because it's just the rotation of the same sigma z. Yes? So it's nothing to say. Now one can also easily find the eigenvectors, which is equally well exercise of first semester algebra, which I will call E plus and E minus, and one can check what it is. It is so that this fellow is cosine theta half, sine theta half, and in the notes you have different sign. I prefer minus sine theta, cosine theta as the other one. Of course, these are orthogonal. Of course, both are unit vectors, and you can check that they are really eigenvectors of this matrix with plus 1 and minus 1 value. As I say in the notes, I have minus here and plus here. It doesn't matter because every eigenvector is defined up to a factor, up to a phase, in this case up to a sign. Why do I prefer this one than the one that I have in my old notes? Well, it's because because when I set theta equal to 0, I prefer to go back to 1, 0, 0, 1, as everyone knows. Yes, for the, with the notes it would be 1, 0, 0, minus 1, so I prefer this one. Okay. So, at this point, I can write what quantum mechanics is telling me about probabilities of finding plus at both ends. As I say, at one end I'm in the direction A, at the other end I'm in the direction B. So what is it? Well, it's a square of the modulus of a matrix element overlap between my 0, 0 state, yes, and plus 1/2 on one side, on one side, and E plus on the other side. Now, it is very easy to compute, yes, because I know what 0, 0 is. I know, of course, this is very simple, yes, it includes this. This is orthogonal. And I know what E plus is. It is written here. It is written here. So, I can substitute, compute, and I don't want to make any mistake now. So I will refer to my notes and write what it is. My glasses on. So it is 1/2 sine squared theta half, where theta is of course the angle between the two directions. Similar calculation for E minus minus gives of course exactly the same. And plus minus is equal to minus plus, and is equal to 1/2 cosine squared theta half. So we know what is the full probability distribution of clicks of these two detectors. Yes, I'm checking what is the spin here in the, so to say, Z direction, and I'm checking what is the spin here respect to z, and check what is the correlation. So these are all the informations. As you can check very easily, it all adds up to 1, as it should, because what else? Yes, that's obvious. And that's quantum mechanics. Now, let's look at the same problem from the point of view of this famous or infamous hidden variable model. What is this hidden variable all about? Well, I have to assume that there is some secret parameter lambda which characterizes each particular run of the experiment, each particular decay of my state, of my excited state that is producing my correlated pair. I have no idea what this stupid lambda is, but what I think I'm allowed to assume is that there is a probability distribution of various lambdas. Some rho which integrated over all lambdas gives 1. And this probability rho determines how often given lambda is obtained when I do my measure, my experiment with a single copy of the system. So, according to classical physics, there should be P A lambda plus minus probabilities and P B of lambda plus minus probabilities. These are individual probabilities. Once lambda is set, my particle with spin 1/2 particle is incoming to my detector, and all I have is to know what are these individual probabilities. So in other words, it is true, or we have to, of course, believe that when we do this experiment with this in this finally hidden variable model, then we still have some statistics, maybe very complicated statistics of correlations, but all these correlations are not due to some magic aspect of quantum physics. They are due to also magic aspect of this rho of lambda. The fact that there is some sort of, at birth, some sort of choice of this hidden variable. Here, yes. Good. So in other words, all these plus AB, all these guys are simply integrals over lambda times PA lambda, say, plus PB P plus B lambda, and so on, and etc. Okay. Now, clearly, all this P plus minus A lambda, all these guys, for A and for B, they must be somewhere between 0 and 1. Because these are genuine probabilities. So now comes something that, of course, I don't remember, namely the form of some numerical inequality which we will prove, which in the notes is called, it is easy to check. Just to, it's trivial. Now I say it's easy to check. I don't remember why did I say this when writing this long time ago. So suppose we have 4 positive, or rather negative numbers, x, x prime, y, y prime, which are all between 0 and 1. And now I have to make sure all my primes are in the right places. Minus. Oops. Better
So the first and the third.
X, y, minus x, minus x prime minus y prime. So let's look at this sort of expression. And do you know how to prove it? Expression. How to prove that this whole combination in this area is smaller than 0. It should be easy.
We could collect some elements.
Look, here is my case. This is my proof. I have no idea how Bell has done his job proving it. This is how I do it. So, look at this expression as a function of x and x prime. Treating y and y prime as parameters. Then clearly, since this is linear in x and x prime, this is a definition of the plane. Yes, it's a linear thing. So this function f is a plane. So let's check what is this value of this linear combination at the coordinates. And let's do this carefully together. So when I put x and x prime both equal to 0, then everything disappears except minus y prime. I'm sorry, there is something wrong here. It should not be y prime. One of them should be without prime. Y. Yes. Okay. So clearly at 0, 0, value here is minus y prime. Yes? So let's check what is this value here. Here x is equal to 0, so this is missing. This is missing. And this fellow and this fellow and this fellow are equal to 1, yes? So what do we get? From here we get y. From here we get y prime. From here we get minus 1. And from here we get minus y. This cancels. So value here is y prime minus 1. Okay? Now, how about this one? For this point, I have both of these guys equal 1. So at that corner, I get y minus y prime plus y prime minus 1 minus y. What happens? Well, this fellow cancels against this. This cancels against this, and I get y minus 1. And finally, this point, I said, now x equals 0. Here. Did I do correct thing before? For this? No, because for that I should drop this, and then y minus y prime minus y, so it is 1 minus 1. No, it's okay. I think something wrong.
The first one is without y.
Here without prime.
No, the left.
Here?
Yes, because you have here.
Correct. Okay, now here once again. So I said x equals 0, this is missing, I get y plus y prime minus y. Once again, x equals 0, so they are gone. Here I get y plus y prime minus 1 minus y prime. This cancels, so I get y minus 1.
So there's, excuse me.
Yes?
I think there's a mistake in this.
In this concept?
Right.
Yeah, probably.
Maybe. So it should be, it is x prime equal to 0, right?
Yes. So I get y minus y prime.
Minus y. So it's minus y prime.
So it is minus y prime, yes?
Yes.
Excellent. All I want to stress is smaller than 0, here is smaller, here is smaller. In other words, it is smaller everywhere in the square. Yes? We are done. Good. So, this inequality really holds. And now, we just substitute. And then again, I will put my glasses. We substitute for x, we substitute p plus of a lambda. For x prime, we substitute p plus of a prime lambda. For y, we substitute p minus of b lambda, and for y prime, we substitute p minus of b lambda. So we write this inequality now with the help of these stupid p's, multiply everything by rho of lambda and integrate over lambda. And this way we get famous inequality, which is the original inequality of Bell. Plus minus AB minus P plus minus A P prime plus P plus minus A prime B prime. 1, 2. Plus P plus minus of A prime B, smaller or equal of P plus of A prime plus P plus of B. Here we are. Now we remember that, of course, these individual guys, they really do not have any correlation property, so they are both 1/2, just as we discussed also in quantum physics. So we have a very definite prediction concerning this combination of correlations for 4 different directions, A prime, B, and B prime, for these 2 detectors, that is only a consequence of our assumption of so-called local hidden variable, existence of local hidden variable. Namely, that there is this rho of lambda, which is really governing the outcome, what is really flying away. On the contrary, according to quantum mechanics, the outcome is determined while particles are detected. And indeed, when I now take our probabilities, all these guys here, it is easy to check that practically for every angle set of these 4 vectors, except maybe when they will go inside, our probabilities in quantum mechanics, all these guys, are violating this inequality. And in particular, one can check that maximum of this thing. I mean, it's enough to point out at a single realization for which this happens, but actually the maximum is obtained when you take equally spaced all these 4 vectors. So A, B, A prime, B prime, and now suppose A is here, then let B be be a biangle theta. Then next, so that is B. The next A prime, same angle. And then finally B prime, also the same angle. Some particular choice. As I say, practically at every non-trivial choice, this inequality is violated, but let's take this. What happens is, when I look at my Bell inequality, then angle between A and B is equal to theta. So I've got 1/2 cosine squared theta half. You remember we computed this. Then let me look at the pluses first. Angle between A and B prime is also theta. So it is again the same quantity. Now let's look at the last positive term, which is A prime B prime. Okay, A prime B prime is also the same. Finally, let's look at the negative term. Now, negative term has angle between A and B prime, and of course between A and B prime it's at 3 theta. So it is minus 1/2 cosine 3 theta over 2. So it is 3 cosine squared, of course. 3 cosine squared theta half minus cosine 3 theta half. Well, one can draw this function of theta. One can check easily that it is actually positive for any theta. And particularly at 45 degrees, when theta is equal to 45 degrees, it has a maximum, and the maximum has a value of, so for this thing is equal to 1.207. Amazing, isn't it? I know that most of you, or maybe even all of you.
Should be 1/2.
What?
Should be 1/2 for
Here.
and here in the right.
Here also, yes, you're right. Yes. I think it's incredible. It means that power of thinking, just power of thinking, tells us that by doing proper experiment, in principle one could distinguish between the local hidden variables and the real quantum mechanics. So it was of course up to experiment to check. This distance between 1 and 1.2 was a bit narrow. So several people looked at some other combinations of these correlations that would produce slightly bigger difference between classical and hidden variable and quantum mechanical result. And there was another similar inequality which has been derived in the paper by 4 guys: Clauser, Shimoni, Holt, and one more. I have it in Holt, yes. Holt and Holt. Okay? And there, the difference is slightly bigger. The classical physics of Bell inequality is in some inequality too, and the quantum result can get to 2.7 or something like this. John Clauser was the very first who attempted to check, to measure possible violation of Bell inequality. And not only because of a gossip, but also because I heard him talking about his early achievements in quantum mechanics, that it is true that he didn't know which way quantum mechanics will tilt, but had a hope at least that it will fail and the hidden variables are there. So, as you know, or you can guess, he got a number which was bigger than 2. In other words, he found violation. But his critics were saying, okay, but your error bars are large, and I don't remember, I think, less than 3 sigma away. He was less than 3 sigma away from the classical value. So of course the probability was very small that actually his result is compatible with hidden variables, but was deemed indecisive, yes. So in 1982, a group of French physicists, with the most famous of them and the first author on the paper, Alain Aspect, did a very similar experiment with the same inequality and with the same cesium atom which undergoes transition, producing a pair of correlated photons, yes, with polarizations being counterpart of these 1/2 particles that we had here. And I don't remember what was the error bar on the results from Aspect, but it was so small compared to the huge distance, then people said, okay, no way. No local hidden variables are there in quantum mechanics. So quantum mechanics won this, perhaps the most interesting, in my opinion, the most interesting test of this randomness, yes, the fundamental aspect of this randomness. Since that time, people looked at various aspects of the Bell inequalities in several different ways. For instance, there was a whole series of papers deriving similar Bell-type inequalities for higher spins. We will not cover it, but I think without reading any of these papers, those who have correct intuitions would guess what sort of qualitative, what sort of results you get when you go to higher angular momentum. In other words, you have more states to work with. I think almost everyone should know that if the spin gets higher and higher and higher, there are more and more states, and everything becomes more and more classical. In other words, for high spin, you also get some violation by quantum mechanics, but it is smaller and smaller, so of course it is harder and harder to test it, and who cares, since the test for the smallest interesting spin, namely a half, has been done so many times. Another aspect of the later history of Bell inequalities is the aspect of so-called loopholes. It is like looking for the loophole, for some reason why this experimented aspect did was not very convincing. And one of the reasons for the initial experiment was the following. Okay, he had to prepare this A and B and so on, these directions of detectors ahead of time. So in principle there was time to communicate by some magic little devil what are these correlations, and then we thought perhaps these set positions influence the source, and source eject these 2 photons in some particular way. That was one of the loopholes. Okay, Aspect knew about it, or was told, or was criticized maybe by referee, I don't know. So in the next range, wave of experiments, he started tossing a coin, so to say. So things were rotating very quickly, and he believed that more or less this A and A prime for the measurement are chosen kind of randomly. A little better, but still, well, people say, okay, this is some kind of the not truly random motion, so maybe there is something in between. And so the quest for loophole-free measurement of Bell violation, in some sense, is still going on. Over the last, say, 2 years, there were several experiments where the distance between these 2 detectors was so high, so huge, that the choice of a direction was really made so quickly that any information traveling with the speed of light would never be able to reach this decaying atom. Okay? That was... Then we have to wait for another unfaithful quantum mechanics critic who would say, okay, but still there is this or that. Maybe something will happen. As of now, I think everyone
some truly random process. Because maybe there was some, I don't know, some being which just set all of universe at the very beginning and it just mechanically evolves.
Well, in some sense, that's quantum mechanics. It started with some kind of a complicated,
Yes, but
so to say, wave function, and then it develops on its own. That is not.
Yeah, but it
All there is a big universe wave function plus the boundary condition.
Yeah. Well, yeah. I did not understand very well your concern or your remark.
I think that's those I don't know those.
But once again, something similar is just assumed by this local variable theory. That there is some devil who is really sitting on the decaying atom, preparing the outgoing photons. Yes. Now that has been.
Yes, but I mean that there could be also a second devil which somehow, very long time ago, decides what will be those directions.
But if you, yes, but perhaps
maybe
maybe there is another loophole in it. But if you imagine, it's not that it has been done this way, but if you imagine again some quantum random process which chooses this direction of a detector, then also that one would have to be somehow determined, yes, deterministic. Then there is no end to it. Then maybe there is another one that is also as random as we can imagine. So, okay, but that's really going in the direction of philosophy, not physics. What is still amazing, what I find amazing is that there is this test possible which can be done in more or less an ambiguous way in experiment, yes. That there is, thank you, that indeed there is no such devil. Okay, but there are some guys who really dislike this randomness of quantum physics so much that they say, okay, all these studies are ruling out only some set of hidden variables theories, those that are defined by this rho of lambda. Perhaps there are non-local hidden variables, yes, that there is something like that depends on both these detectors that is somehow responsible for this inequality. Okay, that could be so, but such a non-local random variables theory, in my opinion, is not any more deterministic than quantum mechanics itself. It's just the rephrasing of the quantum mechanics principles. So I never use this notion of non-local hidden variables. Never. Because in my opinion, this is equivalent, so to say, in complexity or in weirdness, so to say, to original quantum mechanics. Let me add one or two remarks about some other attempts to generalize or actually make quantum mechanics less beautiful. One direction is to look for the nonlinear correction to Schrödinger equation. It's a long history of such attempts. If you add such a nonlinearity, then what is lost, unfortunately, is the linearity, is the principle of superposition, yes. That you have two, if you have two solutions, then the sum is no longer a solution, typically. So this is ugly, in my opinion. And yet there are some distinguished nonlinearities which have some other interesting mathematical properties. Several famous people came up with some ideas. Weinberg had some idea, Gissin had some idea, but we also have a local Warsaw idea. Long time ago, 30 or so years ago, Micielski, deceased, late, and Iwo Białowski, who is still very active, as you all know, had an idea that logarithmic nonlinearity would be interesting. So they postulate that, of course, the Schrödinger equation as we know it, plus there is a term which is proportional to the logarithm of the square of the modulus of the wave function. I don't want to go into detail that within this theory, if something is very tiny, then this nonlinearity would be irrelevant. If things are getting bigger and bigger and bigger, it is more and more relevant, and somehow, at some point, kills the fact that wave function of this guy could be huge, could be much larger than his actual size. Yes. That would shrink with a mass such that would go under, so to say, his body. And they ventured even a prediction what should be the critical size of the object, or mass, I don't remember, of the object for which somehow this nonlinearity would start showing up. And in Vienna, people did the experiment. I don't remember, I don't know, I never studied the details of this. Experiment was with the help of interfering neutrons. So these were nuclear physicists, and they ruled out completely their equation. Of course, they cannot rule out arbitrarily small coefficient, but their upper bound for the size of this coefficient was many orders of magnitude smaller than what our older colleagues were postulating. Yeah. So that's why it did not go into the textbooks. It's forgotten now. Some other generalizations to nonlinearity were criticized very quickly by demonstrating that they would allow for superluminal sending information. And that was also considered completely wrong, so none of them really survived till today. Nonlinear versions of Schrödinger equation do appear in physics. Again, cold atom guys deal with these daily, but these are not fundamental equations. These are some kind of effective equations that are substituting for the true, honest-to-God linear Schrödinger equation for many particles. Yes. Good. That's all about Berlin inequalities. And now my last will be about cryptography. So, of course, we all know what cryptography is. It is sending some information in such a way that it is scrambled in such a way that somebody who could intercept this is not able to decipher it. It has a long history, this cryptography as an attempt to communicate secretly. Obviously, diplomacy was using it all the time. The church, 10,000 years ago, needed this. Military commanders wanted to communicate with their officers secretly, and so on and so forth. And there is a number of ways that you can cipher the information, and they are basically either easy to crack or not so easy to crack. These days, every one of us is using secret communication when talking to the bank or buying plane ticket or something using the computer. This little s in the address HTT, s at the end, is an indication that some kind of a scrambling is used. And the scrambling requires what is called a key. So there is some additional information called the key, which is exchanged between these two sides and helps to cipher and then to decipher. The idea of having such a key being transformed is, in computer transactions, is that the way of deciphering is easy only if you have this key. Otherwise, if you know something special, yes, that is not sent between the two sides. So the idea is that this is, in these transactions, that this is so-called secret information which is part of it. It's not really sent, everything is sent over the open space. Something which is unbreakable, and is being used even now. It's called a one-time pad. Do you know what it is? No. Well, if you have two sides that want to communicate secretly, and each of them is having a sheet with some huge number, million digits, and exactly the same piece of information is on the other side, and then you do a very simple coding of your message by assigning, same on both sides, assigning a number, two-digit number to every letter. Then, of course, if you would send message coded this way, that would be very easy to decipher. Why? Because especially if you know which language was used, then there is and the message is long, then there is a well-known distribution of frequencies, of probabilities of finding various numbers. For instance, various letters. For instance, in English, letter E is the most common and so on. So if this is done all the time of the same substitution, then eventually smart guys will read all the letters. However, if this primitively coded message, which is now a stream of two-digit numbers, is written in between these key numbers, and simple addition is made. And then the result. Then this result can be sent over radio or over a completely open channel to the other side. The other side is simply taking this number and subtracting this key. And then this is the message. One can prove that this way, this stream of numbers, which is obtained by summing, contains only one piece of information, which is its length. So, for instance, if you have two sides, and typically this little guy is telling their headquarters, nothing happens. That's a very short message. And one day, well, something is happening. I don't know, the enemy is preparing for the attack. And then he says, okay, he wants to say, okay, now I see this tank T-34, 5 of them coming from the north, and they are really getting closer and closer. That is a long message. Then somebody intercepting would know that something has happened, because all of a sudden the message is long. So there's one additional, so to say, trick which is added here. Namely, if there is a constant routine communication between A and B, then, and say maybe every evening, then message each day should be the same length. Because as I said, length of such a coded message is the only information which is readable to the enemy. Okay. However, for this excellent trick to work, one has to you need a courier to travel with this key, or you have to be at the same point, at some point, to exchange this book of codes. So this is not good. For instance, with this computer transaction, that doesn't work this way, of course, yes. So people were introducing more and more elaborate schemes. Everyone knows about Enigma, yeah? The Germans had a very nice and complicated way, easy to implement, but very difficult to crack down method of ciphering information. And then there were these famous 3 Polish mathematicians who broke this code, and for a while, until the beginning of the war, Poles were able to read practically everything the Germans, especially military, but also diplomatic mail, was carrying. If one is going to the movies about this stuff done in Britain, then this Polish effort is barely mentioned. Everyone there is talking about Alan Turing, who, by the way, as we play machine. So our guys solved everything with 3 wheels. The 4th wheel was added, and that was adding to the number of combinations in an enormous factor. However, Turing clearly was using methods developed here in Poland, but went, of course, much further. So both his contribution was incredibly important, and his contribution was certainly based on the Polish effort. As historians are telling, practically all methods of coding by Russians, by Germans, and by Western allies, to some extent were broken by the enemies. And there was only one cipher that is believed not to be broken during the war, has not been used much, has been used between some of the aircrafts, carriers, I don't know what well, certainly naval part of the American army operating against Japan and the mainland in the US. And that was kind of, do you know?
I think we know.
Yes. It was actually by use of the Navajo Indians. So their language is so strange and unknown almost to anybody that by placing one of such Navajo guys on the ship somewhere far away and another at the headquarters, and having them first to translate the message to Navajo and then sending it over a completely open channel, and then having another Indian at the other end, was the safest way of communication.
I've also heard that during the 6 Days War between Israel and Arabians, some of Israeli were using Polish.
But that I would say, it could be true, but I wouldn't believe that this is safer than using Navajo. Okay. So much for the
Now we have some things like linguistic Olympiads in Poland, which is basically like translating some Indian languages. So it's like deciphering some code from the Second World War.
Yes, well, okay, so much for the stories. Now, as this transactions at a distance show, it would be great to have a very, very safe way of exchanging or of communicating the key. All this set of ciphers are called open key cryptographic methods. And in 1984, 2 physicists, American Charles Bennett and Canadian Gilles Brassard, had an idea how to communicate secretly using principles of quantum mechanics as a help. Okay? So I just want to tell you now about a scheme which is now called in the jargon BB84. BB for these 2 guys, 84 for the year. BB84. So imagine, as always, we have Alice and Bob, and they want to exchange secret, they want to exchange the stream, huge numbers, a lot of digits, over open channel, but in a way that no eavesdropper, always the bad guy is called Eve, can intercept these numbers. And of course we know that every very complicated number can be always written in the binary system. So all we need to send stream of zeros and ones yes, long stream of zeros and ones from one side to the other. And now, let's do the following. Let's have 4 different polarizations of photons at our disposal. So there will be either vertical and horizontal photons that Alice can send, or those that are rotated by 45 degrees in relation with this. So there are 2 different ways of sending either this photon or this photon, either this photon or this photon. 4 different types of photons are being transmitted. Now, Alice, Bob, of course, knows about these 2 possibilities. Now, Alice, when sending photons, one by one, is choosing more or less randomly. Randomly is choosing from this or from this basis, she's sending photons. So she's sending a stream of photons of 4 different kinds. And Bob is trying to figure out what is she sending. Suppose she has sent just, right now, just a photon in this basis. Bob is choosing at random his basis. If he chose the right basis, then depending on whether she sent 1 or 0, he would get exactly the right thing, of course. If this was the polarization and his basis is right, then of course he gets it right answer. If she chose this fellow, then again. However, if he was unlucky and his polarizer or analyzer was set this way, then of course he's getting zeros and ones, but completely randomly related to this one, yes. If it is 45 degrees and she sent 1 of this type, then half of the time this will click and half of the time this will click. No good. Similarly, if her choice was this basis, again, if this was related exactly to this, then it's fine. If this was related to this, not fine. Okay, now they are sending as many photons as they need, millions or whatever. And then, after this is done, they announce for each photon sent whether she announces whether her base was this way or her base was this way. She's not telling whether it was 1 or 0 of this sort, but she's saying that this sort of photons were chosen. And now, with each of this information, Bob announces, I agree, when his polarizers were arranged exactly the same way as her, and says, I disagree if it was different. Now, every time there is a mismatch between sender and receiver, information is erased. That is no good. However, if polarizers were arranged the same way, then it's a secret thing. Then 1 is transmitted to 1, then 0 is transmitted to 0. So this is fairly nice. It's pretty safe. Why is it pretty safe? Imagine that our Eve has amplifier and is intercepting all these photons, making out of this 1 photon 2 or maybe 52 identical ones. She sends one of these guys here and then makes a lot of analysis with the remaining ones. She has so many copies that she can do God knows how many various experiments to truly determine what sort of photon was it, yes. She can also, having a lot of copies, she can also arrange these polarizers this way or that way, and then she can intercept, or it's open channel, she knows when these guys agreed, so she would also eliminate those that disagreed and so on and so on, and could have the message intercepted. However, there is a beautiful, almost trivial quantum mechanical theorem which is called non-cloning theorem. Non-cloning theorem is, in its most primitive fashion, can be derived in two lines, and I'm going to do it here. It is due to Wouters and Żurek, our colleague from the Sorbonne. And it goes like this. Imagine that we are sending a photon into this amplifier, and of course amplifier must have some whatever wave function, we don't know what. And the idea of using this amplifier is that after it is amplified, there are two H photons, and maybe, of course, the remaining thing is, of course, maybe also somehow altered. Imagine that a photon is nicely amplified to two identical photons. And imagine that also some other B photon by this fellow is also amplified nicely. Maybe this is possible. But now take A plus B, maybe normalized properly, sent to our amplifier. We know, it's a linear theory, we know what A does, that produces AA. What B does, it produces BB. So in other words, this is AA.
Excuse me?
Yes?
First line, what actually is B?
Some other photon. Maybe one is vertical, the other horizontal, perhaps. Some other state of the same qubit in the modern language.
Yes, I know, but I don't understand because I thought that this copying device or something should copy this A to secondary, and that's true. And sample change its own state, right? But it's
Yeah, it's psi and phi.
but it doesn't. It's phi. Oh, sorry.
Phi,
Okay,
yes.
I thought it is B. Yes.
It's not the most general situation. There could be some entanglement, but I'm just writing in the most simple fashion. Yes. Now you see, this is like this. On the other hand, if this combination was copied properly, it should have also the mixed steps AB and BA, yes, or twice this, yeah, which is missing. So in other words, unitarity or linearity of quantum physics prevent copying of the quantum state of unknown nature. Had we known what A is, of course, we could copy it, but we want blind duplication, yes. We want something universal that will copy not only A, not only B, but also A plus B. And that's not possible. So this is really one of the reasons why quantum physics, in theory, is really preventing eavesdropping of the BB84 scheme.
But cannot the first phi be different than the second phi?
Yes, that is of course complication that one can add and one can study, but clearly if this is different, then this is still no good, yes?
Okay.
Because this is even more complicated.
Oh, yes.
Yeah. So I could even write here phi prime, and it would be phi here and phi prime here, and which is even worse because it's not. Yes. Well, not necessarily exactly using the scheme of BD84, but there are very similar analogous schemes designed and advocated by many different physicists. One of the most often quoted is the one devoted by our former student Arthur Eckert, who is now dividing his time between Singapore and Oxford. And I don't want to go into detail. It's similar, somehow Arthur's scheme is similar system where Bell inequalities are tested, but I don't want to go into the detail here. But I want to say that there are several companies that are selling devices which are doing quantum cryptography for you. They are as secure as more or less quantum mechanics says, but not that secure. They are slightly less secure. There are several reasons. On this BB84 scheme, what makes it not entirely secure is the fact that it's almost impossible to produce a stream of single photon states. It's slowly becoming possible, but a device that would really produce one by one in sequence single photons is incredibly costly. That is available probably in 2 or 3 laboratories and takes probably half of this room to produce. So what is typically produced in what eQuantique, a company run by and owned by Nicolas Gissin in Geneva, is doing, is not really having a stream of single photons. It's having a stream of tiny light pulses which are attenuated from the laser beam. And those are more like a little coherent states. In other words, it's not a single photon, it's a combination of single photon plus 2 photon plus 3 photon plus 4 photon with a well-defined phase in between. Yes, I introduced coherent states here, and you heard about coherent states from other sources. And that is already not satisfying all these things. Classical, would it be classical light? Classical light can be accelerated, can be increased by various systems. Whenever you do so, then there is always some noise coming. Amplifiers are known to always add noise. So, of course, even though classical light can be amplified without much distortion, some distortion is always introduced. But still, it's a limitation. Yes, we are not in the setups which are being sold for, I don't know, 5,000 euros or something, maybe 10,000, I don't know, are, so to say, too primitive to really rely fully on this quantum mechanical aspects. There are other ways of attacking this by blinding Bob by showering a lot of other photons, and then it's not very easy to uncover, to distinguish what are the photons that are sent from Alice. Okay, I'm always ending such discussion with a joke, and then also you can just break into her office, kill her, and start sending your own photons. Yes, quantum mechanics is not so foolproof. You cannot really defend her against some direct assault. Yeah. I will add one more remark concerning quantum devices. If I repeat myself, tell me whether I said this already. There are also companies, actually this eQuantique by Gissin is also selling random number generators which are protected, so to say. Their randomness is guaranteed by quantum physics. It is kind of obvious we really spend some time today stressing that this randomness is so fundamental to quantum physics. And in the case of this eQuantique random number generator, everything is based, as far as I know, on the fact that if you've got a single photon and it goes through interface between two different regions of space with different refractive index, then there is, as we know, there is always a reflected wave and transmitted wave. If you have one photon, then this guy also has to make a decision, and this decision, and there is no hidden variable, so it's really random. Yeah? In principle, yes. I know the guy, a very good, also Swiss physicist, who decided to spend a couple of $1,000 or whatever to buy such a device, and then ran various tests of randomness, and he says that it is of course very good random number generator, but not really better than what you have in your Fortran or C library as a pseudo-random generating routine. Yes. So there is always a little bit of the dirt that is put in such a real device over what quantum mechanics is telling, which is making it not completely, not as perfect as theory of quantum mechanics tells us in principle is possible. With that, I think the rest is silence. Who says this as well?
In Hobbit.
Yes. Yes. That's the last words of Hamlet. Let me add then one anecdote. Many years ago, maybe 15 years ago, I was giving a course in Austin, in Texas. And I had fantastic international audience, including a lot of, well, not, some professors. And I chose to finish the same way. And the rest is silence. And then I asked the same thing. Who knows whom I'm quoting? Out of a room filled with about 20 advanced people, there was only one guy who knew. And the guy was American physicist with the Israeli Jewish background. So he went to school in Israel. He was the only one who knew. Americans there, of course, had no idea. Not to mention, I don't know, Latin Americans and some Indians and others. Now this fellow, whose name escaped me now, well-known physicist, he knew and said, but you know what, I read it in Hebrew and I think it is not, and the rest is silence. I think it is what remains is silence. And I wasn't sure because I myself also read it in Polish. And what remains is silence sounds better, yes?
Yeah.
But then we check.